Hello, everyone. I'm Devin, and I'll be presenting bringing the full power of Snapp to embedded programming. So just to start off, probably the first thing that I'll note is that Snapp is a very powerful general programming language with a lot of advanced features. This includes asynchronous events, so you can receive keyboard input for your programs, broadcasted events from other scripts, and various other input-related things. It also supports pretty effortless parallel code execution with multiple scripts executing simultaneously in a really intuitive way that students just pick up right away pretty effortlessly. It supports both declarative and functional programming styles and a bunch of different programming paradigms. And it has some pretty advanced cyclic data structures that you can do with lists, has closures, rings, and a lot of advanced things like that. However, it's historically been trapped running in the browser. This is ordinarily a good thing. When projects run in the browser, as opposed to being an installed application, it gives a pretty consistent user interface, pretty much independent of the device people are using. But it has some limitations, and specifically for us, we're interested in targeting embedded microcontrollers. So the browser is just not going to work for that. And more specifically, we're interested in having students be able to do some Internet of Things related activities, where they'll need to be able to access web-based resources, cloud variables, internet-connected sensors, that kind of thing. So that poses another issue that we'll need to address. Now, there are some approaches for using Snapp or Snapp-like languages for embedded targets. Some existing ones are Snapp for Arduino, microBlox, the microbit extension, and various others. However, for our use cases, at least, these usually fall into one of two problem categories. So one of the categories is projects being full Snapp, but they're still running on the computer. So this includes basically any project that will just have a command execution REPL basically on the microcontroller. And you're not actually running your code on the microcontroller, you're just communicating with it over Wi-Fi, Bluetooth, serial, that kind of thing. But the issue with that approach is that if you close the browser tab or turn off your computer, the project stops running. So that'll be a problem for some of the use cases we'll talk about later on. Now, the other problem area are those that actually do run on the embedded device, but they're not running Snapp anymore. So this includes projects like microBlox. Basically, there are some projects that have a block-based language that's kind of Snapp-esque, but is not Snapp itself. The language itself is designed to be simple enough to compile on an embedded target. But we want to go the other way. We want to start with Snapp itself. We want to keep all of these advanced features that students are already familiar with and just be able to use the same language, but now on microcontrollers. So where do we go from this? First, we need to identify a language that's very close to Snapp and has all of those advanced features, but still has a little bit of the stepping stones toward the IoT experience that we want to provide for students. And so we're going to go with NetsBlox specifically. For those of you who don't know, NetsBlox is a fork of Snapp that adds just a few networking features on top of what Snapp already provides. One of these are remote procedure calls, or RPCs. These are like this call block down here. Through the collection of drop-down menus, you can pick a service in the first drop-down and then an RPC in the second one. And it allows you to invoke specific effects on the NetsBlox server. So some of these, like the one shown here, just access a data set. For instance, this one is pulling CO2 trend data from the Mauna Loa CO2 data set. And that just is returned to your project as a list of lists, and it's like a time series of CO2 concentrations. So that kind of thing. You can just really easily pull web APIs down from the server.
Habt ihr Wasser getrunken in letzter Zeit?
Oh, sorry.
Merit? Magst
Go ahead.
Okay. NetsBlox also provides message passing between projects. So you can make a custom tagged data type like my data type with fields X, Y, and Z. And then you can just pass these dictionaries of key value pairs between projects running anywhere in the world. So this allows you to do some Internet of Things type of projects and distributed computing which we'll be needing for the eventual use case down the road. NetsBlox also supports some other features like real-time collaborative editing, which help with students working together on projects simultaneously, kind of like Google Docs. It's important to note that aside from adding these networking features, NetsBlox is identical to Snapp. And so if we build something that works to run NetsBlox code on embedded microcontrollers, it also runs Snapp code. Now, NetsBlox is a pretty good platform for teaching introductory IoT, and we also already have some projects that do this. For instance, you can use these RPCs and message passing to communicate with personal smartphones that students have. You can just connect those to NetsBlox. Also, some physical and virtual robots in like a little robotics environment. And we have various other related activities like that. We just need to address the microcontroller problem, but otherwise this has the IoT features that we're interested in. So how we're going to do this, we have decided we will build a new runtime for Snapp and NetsBlox code from the ground up. Now, this is a pretty big undertaking, so if we're going to do it, we want to do it right, and we want to do it once. So because of that, we've picked the Rust language as the language of choice for designing this. And specifically, we picked no standard Rust, meaning it doesn't rely on the Rust standard library, which allows it to run on pretty much any platform targeted by the LLVM backend compiler. So some of the targets supported by this are web. So we could actually compile this into WebAssembly and run it in the browser. We could also compile it for a server, desktop app, mobile app, anything of that nature as an actual like native installed application. But the one we're interested in is the embedded space. So this needs to support all of the advanced Snapp features that we previously talked about, as well as NetsBlox features specifically. So this includes asynchronous execution of blocks, parallel execution of scripts, recursion, rings, watchers, events, all the networking features of NetsBlox, just all of those things. And we need to architect it specifically with customizability and extensions in mind. Different devices might have different ways of talking to hardware peripherals, so we'll need to be able to add in additional code for different platforms. Like phones will have a different interface with the hardware than the laptop will, and especially from embedded devices. So we need to keep that in mind. But importantly, once this is all done, now users can write a single project in NetsBlox or Snapp, and it'll run on any of these devices subject to what hardware peripherals are allowed. So specifically, we're going to be looking at the ESP32 version. So this will actually be compiled and flashed directly onto an ESP32 microcontroller, which you can see here. The board will then host a NetsBlox extension that you can import in the browser, and you can use that to control the device. So this will load up a new tab of blocks called native, which has any hardware-based blocks. Chiefly among these is the syscall block, which is the hardware analog of NetsBlox RPCs with the call block. So you can see with this drop down here, you can just pick display set pixel, and then you can set a pixel by its like X and Y position, and then like RGB values for which color you want to set it to. And different peripherals have different functions, and they're all together here in the same style as RPCs. After this extension is loaded, users can write whatever Snapp or NetsBlox code they want to run on the device. So that's just all normal in the normal editor, and most things are supported. From there, students can actually upload the code that they've written to the device with this embedded terminal that's built right into the IDE by the extension loaded by the board. And they can also send the device the green flag, play, pause, stop signals, and that kind of thing, and receive output. So how does debugging look in this scenario? So first of all, program output like say blocks and any errors are going to be displayed in the terminal window that we just saw. So in this example project here, we have some say blocks that'll be printing out some lists. So the microcontroller will run that, get the output, and send it back into your browser so you can view it. And errors will also show up there. Now, if errors were only shown in the terminal, this would be pretty hard to debug. So they are also shown as little red error comments that are attached to the specific location. So this is a single error, but the error comments together form a stack trace. So you can basically see where the error started, and every step along the way, it gives more information. And you can see on each one, it provides a full snapshot of all the variables that are in scope. So on this one down here, you see A equals 516, B equals 6. On this one, you see different variables. And it's just everything contextually in that stack frame. So that makes it a lot easier for students to debug. They don't have to wonder what values were when an error happened. It already is recorded for them. I should also note that a connected browser is not required. If you close the browser tab, the microcontroller will keep on executing the same project it was, and it'll just cache any output and errors in buffers for the next time a debugger connects to it. NetsBloxVM also supports some other things like the pause block in control tab for a sort of breakpoint students can add to their code, and also watchers, though those are not integrated into the extension quite yet. So as far as setup goes, the board hosts a configuration page, which can do a few basic things like manage the Wi-Fi access point for initially configuring the device without internet connectivity, as well as the actual internet connectivity. So for the networking features, you'll actually need to connect the device to a Wi-Fi network with internet. So you can do that through the setup page. But the important one is this peripherals. So currently, the way you add hardware peripherals that students can access is you edit this JSON file that's stored on the device's flash memory. So we're looking to make this part a little bit more intuitive for students. Currently in this form, teachers might need to help students, especially younger students, to write this. But you can see basically you just configure like an I2C bus here on specific GPIO pins, and then you give a collection of motors, and they're on specific GPIO pins, and then some other sensors here. This is an ultrasonic distance sensor, and this is an 13:9 RGB LED matrix. We'll see both of these in the demo part later. So you can just upload this peripherals config to the device, and it'll add them to the syscall menu in a convenient way that students actually can use. I should also note that this is an entirely wireless experience with no flashing needed. You don't need to flash the board with new firmware if you change the project, if you give it new control signals, even if you change the peripherals. You don't need to ever reflash the board after you receive it. So let's just see this in action now. So I just have this little pre-recorded video where we have a simple project here that is generating a sine wave and plotting it on a 13:9 RGB matrix, and it's like oscillating the color. And I'll just make a little change here. I'll increase the frequency of color oscillations. So I just upload that to the board and send it the green flag signal to restart. And here I'll do another short edit here. I decrease the amplitude of the sine wave from 3 to 2, upload it, restart. And you can see the change just takes place right away. And then I'll do one more decreased amplitude to 1. And just to really emphasize that this really is running on the microcontroller, I can go ahead and actually close the browser tab that NetsBlox was open with. And I can even put the computer to sleep. It doesn't matter. This is still going to be just running entirely on its own on the microcontroller, that same Snapp code that we provided it. And then also, if we go back to the configuration page for the board, it'll just have a link we can do to open the editor with the extension already loaded. So you just load that up. And then we can go back and reopen the terminal. So in addition to the upload button, there's also a download button. So you can actually get the project that was already running on the board and open it back up to continue editing. Also, projects are persistently stored on the device. So if you turn off the device and turn it back on, it'll start running the same project that you previously loaded onto it. So here's another project where we're just going to be using the DC motors peripheral. And we're just going to go forward a little bit and then turn, forward a little bit, turn 6 times, and it should go in a hexagon and arrive back where it started. So we just uploaded that to the board, hit the green flag to give it the start signal, and it just takes off. So just to show another little edit, we'll just make it a smaller hexagon. So we'll decrease the amount of time that it's going forward. and we'll just upload that to the device. It takes place immediately. We just give it the green flag, and it goes right ahead and does it. So we can really just run the Snapp code directly, and there's almost no time in between writing the code and actually running it. And here's another little example that's using the timer blocks. So it'll basically go forward until the distance sensor reads something less than 15 centimeters. So it's about to hit the wall. And then it'll just go backwards for the same amount of time that it was going forward. And it should stop just about where it started. So as far as some actual IoT projects, here's one that uses the BMP 388 environmental sensor. So it has a built-in pressure and temperature sensor. This project will read pressure and temperature 10 times a second and store them in a list. And then periodically, it will use the cloud variables set variable RPC for NetsBlox. And it'll actually save all of the data that it's aggregated to a cloud variable with a specific name that we chose. So here, I'll just take the device upstairs. The pressure sensor on this particular environmental sensor is very high precision to the point where it can actually be used as an altimeter even. So we should see a pretty significant pressure fluctuation when we get back and look at the data. So I'll just take it down here to the ground for an even bigger change. And then we'll go back to the code. Okay, well, we don't need any more data, so I can send it the stop signal right here. And now I have this separate project. So this one actually is running in the browser, this part of it, just for plotting the data. So this will just grab all of the content of the cloud variable, and it has just a few more blocks that will use some various NetsBlox RPCs to plot the data and visualize it in a graph that you can use with the switch to costume block. And you can see the pressure decrease there when we went up the stairs and then back down. Okay, well, that's pretty much all I have for the demo section, and I just have a few more references here. But thank you for listening, everyone, and I can take any questions if anyone has anything.
Devin, you had a few questions.
Oh, yeah, I'm looking at the chat. Oh, yes. So the it's not the style where it will send commands. Like each time you hit a syscall, it doesn't send a command to the board. It actually sends your entire project to the board. And then there's actually a compiler. I didn't mention this part, but when you send a project to the board, you're actually just sending the XML serialized version of the project. And then there is a compiler. The compiler will turn the XML project into NetsBlox VM bytecode, basically. And the compiler is actually so small that it can fit on the microcontroller itself. So all you do is send the XML to the board. The board itself will do all the compilation and linking, and then it'll interpret that bytecode right away. And it's just, really fast. Let me see. How long does it take to upload bigger program? So we don't have a speed for how long it takes to upload programs, but the compiler itself, I've never seen it take more than like a second, even for some of the larger programs that I've tried it with. Even if you have a pretty big project, usually it's only big because of images and graphics and things, and those kind of things wouldn't really make sense on an embedded platform. So you would have to have just a big project from lots of code, which is less common or less of a problem. But extensions, someone asked if extensions have to be written in Rust. So if you want to add a new type of peripheral, like I've added support for DC motors and like RGB matrices and various sensors and those kind of things. So if you want a new type that's not already supported, that would have to be in Rust. So I actually did have an example of rings and reporters. I don't know if I really have time to go back, but if you look here in this first project, the sine wave we're plotting is actually stored in a variable called f, and it's actually a ring. And it's there's the call f with inputs. So it's actually doing that. You will at some point hit a stack limit, but that will actually be caught by the virtual machine. It has its own checking for that. And I think I'm out of time. So any other questions I can answer in the chat. Okay, but thank you.